So this was the assignment. Were you able to do the first question, or did anyone have a problem in this? Can speak up. Okay, how many of you were able to do, say, first part of the first question? Just raise your hand. Am I audible? Yeah, I think I am.
Yes, we can hear.
Okay, great. So, okay, I'll simply ask people because people are not replying, and I think it's better that I call out people. Bevan, were you able to do the first part of first question? I mean, what do you think it is? What does the function look like? Yeah, can you make a guess?
Like I did it, but I don't remember it well now. So I think the second one looked like a parabola.
Yeah, the second one looks like a parabola. What about the first one?
I think the first one was linear.
A linear straight line,
yeah.
Right? Yeah. So, okay, that is correct. We can simply, try plotting one of these. So, how should it look like? Like, what should it, how should it look like? So, a straight line. How did you come to know that it's a straight line?
So, I don't remember the equation well, but for the first one, I think for x is equal to 0, I got r equal to y is equal to r.
Okay.
And also
yeah.
I'm not remembering exactly what I did.
Okay. Okay, it's fine.
When you differentiate, you'll get a straight line graph, something like y is equal to mx plus c kind of a thing. That's why it's a straight line.
Yeah. So if you look at the function, it looks like fx equals r times. I'm just opening this up, okay? R minus, it is rx by k. So in a sense, it looks like y equals some c, which is a constant, plus minus of r by k times x. And we know, I think Shoaib must have covered this in the last tutorial, that this looks like a what do you say, the function of a straight line. This is our, yeah. So this is our c, this is our m times x. So whenever you see that the power of x is 1, here the power of x is 1, I mean, you're sure that this is a graph of a straight line. This is a function of a straight line. But how would so now that I've written it like this, how would the slope of the function look? Would it be an increasing function? Would it, go from here or here? Would it be a decreasing function? What do you guys think?
It would be a decreasing function.
Decreasing function.
Decreasing function.
Decreasing function. Why? I mean, what information did you gather from the function?
Negative
so slope is negative. M,
Great.
The value of m is negative because r and k are both positive.
Okay, so where does this, and where should I make the line? Should I make it here? Should I make it here? How do I choose that? Where should I make that line?
We equate first we'll equate x is equal to 0 and then see what the value of y is. Basically, we'll try to find out y-intercepts and x-intercept. So
great. Yeah. So what we do
wherever the equation intercepts x and y axis, we'll find out those values, and that's how we'll.
Yeah. So just to know where, what would be the, so these are very, simple tricks that you can try. You can put the value of x equals 0. When x is equal to 0, your y is c, which is here r. So we know that when x is equal to 0, my y would be some r. And I know from the slope, so this is our y when x is equal to 0. And from the slope, we know that the slope is minus of r by k. And in the question, it is given that both r and k are greater than 0. That is why we can assume that the slope is negative. Great. So we are done with question number 1. Or I think there's another part to it, which says find the zeros. That is the values of x at which y is equal to 0. So for the first one, what would be the value? Did anyone find it out? Abhishek? I'm just randomly calling out names.
Yeah, I have not yet done these assignments, but
Okay,
you could just
you can try.
substitute the values, right, and find
Yeah.
the values of
So
0.
what should I substitute here?
If r is equal to 0, and then
So
r
you
is
have to
greater than
find
0,
the
right?
zeros.
Yeah. So x is equal to 1 for the first equation.
X equals 1. Are you sure? So you have to find the zeros. That is the values of x at which y is equal to 0. So
Oh, I see. Mm,
so what should I substitute?
yeah, can you just leave it at this? I'll just see the equation.
Yeah,
Just
sorry.
tell you.
Yeah, it's okay.
Thank you.
Anybody else? Yeah, Mahesh, go ahead.
Yeah, so we can equate y equal to 0 in the equation.
Okay, I'll equate y equals
Put the value
0.
of y as 0 and then see and solve it. Yeah,
Yeah,
equals
so,
r minus rx by k.
so what do I get is
R equals r x by k, and then r is cancelled.
so yes.
Then you're left with x equals k.
Yeah. Okay. So this is what we get. X is equal to k. So this is one of the zeros of the equation. Great. We are done with the first one. Okay, we'll just continue with the question 2 also, because we anyway have to solve it for both the parts of question 1. So finding maxima and minima of the functions. So how do you find the maxima and minima of the function? Can somebody else tell me? I would like to call Pratik. Pratik, do you remember how do we find the maxima and minima of the function?
Okay, I think I can't answer this.
Okay, it's okay. This is just a practice question. I mean, if you haven't done, I would really suggest that you do this, because we will be using these equations in the course in the next class, hopefully.
Okay.
Okay, it's okay. Yeah. Shri Subha, would you like to try?
Hey, so the first function, I had some trouble. I
Okay.
could get the maximum of the second equation.
Okay, it's fine.
In the first one,
Yeah.
I got a
Hmm.
the first derivative was negative.
Yes. Yeah.
And the second derivative was 0. So does that mean it's like a sad point? And I googled, and people said if you don't get a
Hmm.
without a constant, if you don't get if you don't have a variable in the first derivative,
Hmm.
then by this method you can't figure the maxima and minima.
Yeah.
So I didn't
So
know how to go with that.
Yeah, you're correct. So yeah, okay, the first part is kind of tricky. I'll just do it for you guys. So we know that how do we? So I just want to go through the process of how do you find the maxima and minima. Okay, so the first thing you have to do is you have to do you have to differentiate the function, that is d by dx of the function fx. This is also written as f dash x. You might have seen in other places also. Okay, so how do I do this? I just differentiate this equation that I have. So I get, so when I differentiate r is a constant, so that does not give me anything. That's, so when you differentiate it, it becomes 0. When I differentiate x, I get 1, and I get r by k. Now the first derivative is anyway negative. Okay, so usually when we have to find usually when we have to find the maxima or minima, we usually find it at a point, okay, which is the 0, which is this point. Okay, but here you can't put the point anywhere because there is no dependence on x. We have kind of lost the x. So even if you do, differentiate it again, for example, you take the double derivative of the function. This is written as f double dash x. You get 0 because this is a
0.
constant. Exactly. So here, think about it. You have a straight line. Okay. The straight line, I mean, here I've plotted it as, just this much, but the straight line will continue exist, extending till infinity and even beyond, So you really can't find the maxima of this function or even the minima. So in a sense, the maxima, if you see the global maxima, like over its entire range, over its entire range, the maxima is, lies at somewhere at infinity, but infinity is not defined. So you really don't get any information from this kind of, analysis. So yes, in the first question, the global maxima would be somewhere at infinity, and the global minima would be somewhere at minus infinity. But if I have to just think of my biological question, the function can take maximum value as r. Okay. Similarly, if I just think of my biological function, for example, this is something like some population, or this was what, some population or something. This is like, this is population growth. Okay. And this is my number of individuals, that is the population. So these can't be negative. Okay. So in a sense, the local minima and the maxima would be just these things. Okay. What would be the value of this point from the function? So in order to find this point, you will, here at this point, your y is equal to
It's
0.
0. X is equal to 0.
So
For-
x is equal to k. Exactly.
Yeah, K is written here.
Yeah. So in a sense, yeah. So this is more like a qualitative, because this analysis doesn't really yield anything, right? So that's what the thing is with straight lines, because they extend towards infinity. It's not really defined. It's not a defined point. Where is the global? When I say global, it means, like, for example, if you extend the whole graph to, like, the straight line can go as long as it wants. It's not a defined point where it reaches the maximum or the minimum. Okay, so we're done. So does anybody have a question with respect to this? Just be comfortable with this notation because it might come around in future also. So when there is 1 dash, it means it's a single derivative. If it is 2 dash, it's a second derivative. 3 dash means it's a third derivative. Yeah, like that. Okay, now we'll do the second question. I think second question you guys would be more comfortable with. Okay, cool. So the second question, would anyone like to tell me how would this look like, and how did you even come up with the plot? I think the most important part of this exercise is how do you even think about plotting these plots? What goes in your mind when you think that I have to plot this function? So my function is
You have to give values to it.
Rx times 1 minus x by k. Yeah. I would like to ask Amanda. Amanda, are you there? I'm just trying to see that, are you able to work through these exercises or not?
So here this function is x square, which means it's going to be like a polynomial function, not a regular.
Sorry.
Then we'll go on to Can you
Yeah,
hear
your
me?
voice is breaking. Yeah. So what is the first thing that you, so whenever I give you a function, what is the first thing that you should find? Like think of, what is the first thing that will come to your mind, that if I have to plot this function, what should be the first thing?
First, what the power of x. So if not one,
Okay.
means it's not a straight line. Then it's going to be a polynomial x squared one. Then I went to look at the roots.
Okay, so first you look at the power of x, and then you look at the roots. Yeah. So yeah, I think roots is a very important point. Initially you should look at the roots, I would say. I mean, yeah, power is obviously important, and the second most thing would be roots. Okay, so what are the roots of this function?
I guess I'm
0,
losing
0.
So I don't know who replied. So one is 0, 0. Great. Okay, because if I put x equals 0 here, fx becomes 0. Correct?
Yeah.
Okay. And what is the other root?
So I actually assigned values for r and k. So anyway, the question said r and k must be greater than 0. So I took it as 1. When I did that, at x equals to 1, again, I got f of x is 0.
Okay. Yeah, that is when you have assigned a value. But if I, yeah, so the thing is, I basically, you just equate this to 0, and basically this becomes 0. Sorry, I think I prefer this one 0. Okay. So you know that, okay, so this is another way to look at the function. Okay, so when I know that two things are the product of two things are 0, that is, say this is my a is rx, my b is 1 minus x by k. So when would the product be 0? Either when a is 0, or when b is 0, or both are 0. Okay, when would rx be 0? It would be 0 when x is equal to 0,
X is
because
equal to
we
0.
know that r is greater than 0, which is given in the question. And now the other case would be, for example, our rx is not equal to 0. Then we look at the b here, this b. So that means 1 minus x by k is equal to 0.
Then
That
x
means,
becomes k.
yeah, that means the other root is k. So it's a very, this is a useful thing that you don't really have to solve, and then, so this is like the simplest notation to actually find roots, because it is already, what do you say, represented in a way that you can easily just look at the function and say, oh, the roots are 0 and k, because you think in this way, like the a and b kind of thing. Is this clear?
Yes.
I hope it is. Okay, so my other root is k. So I know at both of these points my function would be 0. My fx is equal to 0. Now yeah, because this is like a parabola, we know that this function would look something like this. Okay, this looks really bad. Yeah. Okay, so I know that this now looks like a parabola. Okay, so part of the question was to find the roots. So we have found that the roots of the equation are x equals 0 and x equals k. Now the second part of the question is find the maxima and minima of the functions. Now, for example, you didn't plot this graph. How would you find the maxima? So now I think it's very easy to tell which is the maximum and minimum of the function. But if you hadn't plotted this graph, how would you find the maxima or minima of the function?
By differentiation.
By differentiating. So I would differentiate it. So this is like the first derivative. So I'll differentiate this equation. I get r minus what would be the derivative of x square?
2x.
2x. Great. So it is 2rx by k. So we know that whenever there's a minima or a maxima, okay, so this is my say minima or maxima, there the derivative or the slope of the function is 0. So we would equate this to 0. So when it is 0, when would this be 0? It would be 0 when say r is equal to 2rx by k. So we know that r is so to solve this, we know that r is greater than 0. So we can just simply cancel this. We know that r is not equal to 0. So we can cancel this and we get x equals k by 2. So this is our solution for the, so this is where the minima or maxima occur. Okay, but we don't know yet whether it's a minima or a maxima. So what do I do next for finding whether it is minima or maxima?
So
We
you
will
take the second derivative and then see if that's positive or negative.
Great. So I'll do the second derivative, which is I differentiate this equation. So r is a constant. So derivative is 0. X derivative is 1. So I get 2r by k. So basically my second derivative is negative. That means this function has a, what does it have?
So it has maxima.
It has a maxima. Great. So it has a maxima at k by 2, which is here. And this was our k and 0. Great. We have actually kind of done this also. And this is very evident by the graph also, the plot of the function. Okay, so we are kind of done with this. We're done with this. Does anybody have any questions about, and we have also done this, any of these questions? Okay, I'll take that as you guys know everything. Cool. I will next move. So I would really agree that the third question is not that easy. If you weren't able to do it, it's okay. It's completely okay because it's not easy, to be honest. So the question says that you have to plot both of these functions in the same graph. Okay. So we already know that the function of this fx rx 1 minus x by k, we have already solved that the graph of this function looks something like this. Okay, now we just have to think what these other functions look like. So the first function is gx equals hx. Now from what we have already learned, can you tell me what would this look like, the gx equals hx function?
It's a linear function.
It's a linear function.
X equals to y kind of graph.
Yes, exactly. But here we have, yes, correct. We would have a,
yeah, it would be translated by x probably.
Yeah, so here, what is the slope of this graph? So we know it's a straight line, right? Yeah. And what would be the slope of the line?
H would be the slope.
Great. H. Does it have any intercept?
No.
No.
No, it doesn't have any intercept. And the question says that H is greater than 0. So how would this look like? Would this be an increasing graph or a decreasing graph? Increasing line or a decreasing
Yeah,
line?
it would be increasing. It would
It
be
would
in
be
the first and the third quadrant.
first and the third. Okay, yeah. The third quadrant really doesn't matter in our case. But yes, correct. That is correct. So this is my GX line. Now we don't really know what is the slope of this. Okay, the graph could look like this. The graph could look like this. The graph could look like this, depending on what the value of H is. Okay. Now the question asks. Oh God. Okay. Are you able to see my screen?
Yeah.
Okay. For some reason, my laptop has gone to sleep. Okay. So the question says that you have to find the points of intersection of these two functions. Did any one of you try this?
I did, but I took values for R and K and then played around with a constant. So that was pretty easy. I didn't do it keeping the constant.
Okay. So the point of this exercise. Yes.
Yeah, Tanveen. Yeah, so I tried equating the two functions.
You tried equating the
And
two
then,
functions. Yes. That
when
is.
we equate hx equals, when we do that, then we just have to isolate x. And then for all the values of x which follow the whatever equation you get, those are the ones which are the points of intersection.
Yeah, that's one way of doing it. Yeah, I was actually wondering if anybody of you tried that. So one way is to actually, how do you find points of intersection of two graphs? You actually equate them. You equate them because the value of these two functions would be same at that point. For example, I know that two lines are intersecting. Wait, I think I'll just rub off some of these. Yeah. For example, I know that these two lines are intersecting at this point. So I know that there would be some x at which both of their y's are equal. So that is the point of intersection of these two functions. So one way to do is that you equate these two equations. So when I equate these two, I take this function to the left hand side and then equate it to 0. So I do hx minus rx times 1 minus x by k equal to 0. So now from this I can take x common, which gives me h minus r 1 minus x by k equals 0. So again, we do the same thing. We know that there is one a and there is one b, and we know that when we multiply these two things, this gives us 0. That means either a is 0 or b is 0 or both are 0. Okay. So one of the solutions is that x is equal to 0. Okay. Now I do b equals 0, which I will do here. So my b equals 0 is h equals r. What did you find from this?
H by
It would be something like h by r. You can do it 1 minus x by k. And then I have x by k equals 1 minus h by r. Then I multiply this on this side. So this is my other solution. Okay. So this is this is the expression of how to find the value of x, the other root. Okay. Where do they intersect? So this is one way of doing it. Okay. So there's another way of doing it is through graphically. Okay. I'll tell you why sometimes doing graphically is much better than doing it like this. So let's also plot this graph. Right now I'm not plotting the straight line. I'll just plot the parabola because I know that the parabola looks something like this. Now I want to vary the slope of the straight line. Okay. So can you tell me how many, depending on the values of h, how many points of intersection can I expect? So I'll just give you an example that that my straight line could go like this. Okay. My straight line can go like this, or it can go like this. Okay. So here, how many, points of intersection can I expect while I am kind of changing the slope of the straight line? So my line could go like this, or something like this, right? I can actually change the h, that is the slope of the line. But how many points of intersection can I expect?
2.
Max 2.
Maximum would be 2, correct? What would be the minimum?
1.
Minimum would be 1. Good. When would the minimum happen?
When h is very high.
Yeah, so when your h is somewhere like this, okay? So it only intersects at x equals 0. There's also a point where this straight line is actually tangent to your plot. Okay. Okay. But the thing is, if this line, if the h, so basically in this direction, your h is increasing. In this direction, your h is decreasing. Okay. So after this point, when it is tangent to the plot, that means around, along these points, okay, you will find that there are 2 points of intersection. One would be this, one would be your x equals 0. But along these, values of h, the number of points of intersection would be only 1, which is your x equals 0. But can you tell me, it might be a little difficult, but can you tell me what would be the value of that h, which kind of demarcates that beyond this you get 2 points of intersection versus 1?
Is it like taking the derivative of the polynomial function?
Exactly, correct. Excellent. So this is exactly, so we know that we get a tangent to for example, this is, so this is some curve that I have, and at some point at this curve, you have a tangent. At this tangent, your dy by dx, that is the uh, first derivative, is equal to 0. So we know that at this point, I know that the first derivatives of the uh, function would be equal to, both the functions would be equal to 0. So what I do is, so basically, I need to find that what is the slope of, can anyone tell me what would be the slope of this parabola at this point at x equals 0? Can anybody tell me that? you know how to take out the slope at a function,
R
right?
minus 2x r upon k.
Yes. Yeah, we did that
Yes.
f dash x, right? Yes. So it was r minus 2rx by k. This was my f dash x, right? So when I put x equals 0, the slope of my function is r. Okay. That means here at this point, since both the slopes are equal, that means my h is equal to r at this point. Okay. So from this analysis, I know that when h is greater than r, okay, which is when h is greater than r, okay, which is this region. When my h is greater than r is this line, okay. When my h is greater than r, I know that there is only one point of intersection. Okay. And when my h is when my r, which is this line, I think I should, yeah, when my r is actually greater than h, or all the values of h, we know that we have two points of intersection when my r is, or I can write it as h less than r. So you have 2 points of intersection. Is this clear? I hope I didn't rush through the explanation. So the thing is, when you actually have h, which is when you have basically in this region, when your h is less than r, that means the slope of the line is less than the slope of the tangent to the parabola at x equals 0 is basically the slope of the line is less. You have 2 points of intersection, and the points of intersection would be many, because think of this line. Okay, this line could go like this, and it could actually intersect every point in this. So you would have many points of intersection. I mean, if my h is not constant, for one value of h, you have only 2 points of intersection. So that would depend on the relation between h and r. This. Is this clear?
Yeah.
Yes.
Great. Okay. Now we'll go to the second one. So we are done with this. Okay. Now second one is a little, it's not very easy, but I would really like if you guys would try. So first thing, we'll just plot the graph of gx. Okay. So my gx looks like hx x plus x naught. Is this correct? Yeah. So okay, I'll start again with the same. How do you even go about plotting this graph? What would be the first thing that I should look for?
You should find the domain and range of the function.
You should find the domain and range. Okay. What would be the domain of this function?
All values of like r minus this x plus x naught becomes 0.
Okay, wait. What are you saying? Okay, how did you find the, yeah, I think so. The thing is, we can have two approaches, okay, to find the points of intersection. Either you can go, actually treating these two, say this gx and fx separately, that I plot gx first and then my fx, or I can just do something like this. I can equate both of these to equate both of them to each other and then try to find where it is equal to 0. So these are two approaches that you can take. Okay, for this one, which one do you want me to go with first? Do you want me to equate these two functions to 0, to each other? Or should we go about plotting? I think plotting would be more interesting because it's a good exercise. So how do you even look at a function and then plot it? We'll also try that.
Plotting is better.
Yeah. We'll also try that approach, but let's do plotting first. So how do I plot this? Somebody said that we should look at the domain and range. So what all values can x take? Somebody has to answer it. So, yeah.
All real values minus x naught.
Yeah, exactly. So x is an element of a set which goes from minus infinity to minus x naught, open bracket, union. So this is just a way of writing x naught to infinity. So open bracket means that I'm not including this point. Okay, just remember that. You can't really include infinity because infinity is not a defined number. It's just a like an abstract number kind of a thing. Okay, but anyway, we are not going to deal with, so we are anyway dealing with this part, which is, we are anyway dealing with positive values of x, right? Because x is our population, say. So in a sense, I can take all numbers as long as it is positive. Okay, so this is our domain. Range, I think range is a good question. What do you think how do you go about looking at the range of this function? What do you think? What are the values do you think this function can take? Let's just look at, say, x by x plus x naught. How would you look at the range of this function? Sorry, basically what all values can gx take? I would like somebody to
natural numbers.
Yes, it would be natural numbers, but still, so I think a good way of looking at a function is, especially when you have, like as a fraction of something, it's a good way to look at it is, for example, my x becomes very large. Say my x is tending towards infinity. Okay. Or x is any value, say 100 or something like that. Okay. Say 100. Okay. And my x naught is, say, 1. So this becomes 100 by 101. Okay. Similarly, I put the value of x to, say, 200. Now this becomes 201. And if you actually see, if you see the decimal value of this, you would see that as x becomes very, very, very large, okay, it becomes very large, this x naught becomes very insignificant in front of it. Okay, so this whole number, this x by x plus x naught, would actually be trying to go towards the value 1. Okay, but the thing is, the denominator will always be greater than the numerator. That is my, so that means my denominator would always, even if it is going towards infinity, even then, even though infinity is a really big number in front of 1, this would always be trying to go towards 1, but it would never reach 1. So we know one thing from this information, that this would be less than 1. Okay. The value of gx would be less than 1. So I would just simply mark this as 1. Okay. So I know that around when the value of x is, very large, say somewhere over here, my function would be tending towards, like how you have the exponent, it doesn't really go to 0. It just, it is always tending towards 0. So similarly, when my value of x is very large, I know that it would be somewhere trying to tend towards 1. Yeah, something like it shouldn't be a straight line, but yeah, a curve like thing. Okay. Now, next, what would do you think? So I think, yeah. So one was, so we are kind of done with the domain and range, okay, of this function. We know that it would be as long as x is greater than 0, the gx would be greater than 0. We know that. But we also know that gx would be less than 1.
Less than 1.
Yeah. Now, what we want to know is, so because we know that it's greater than 0, that means the function should lie somewhere between here, right? It has to reach this point. So now the next question is, we need to know how would this rise be? Would this rise be like, it could be like this, it could be like somewhere like this, it could be like somewhere like this. We don't really know how this function would rise, okay? So I'll tell you 2 ways of doing this, okay? Again, we will look at our function. My function is this. So I can write my function as x times 1 by x plus x naught. Okay. Again, I have, made it look like a product of 2 different functions. The way we were doing that a into b kind of thing, we have kind of divided our, split our function into the product of 2 functions. So this is the function of a straight line. Okay. And do you guys know how does the function of 1 by x look like? So this is kind of like 1 by x, but it is kind of translated. So it kind of looks like, I think it looks like this. Yeah, something like this. Okay, sorry. So now what we do is, so this is just a trick to, how do you even plot functions like these. So basically I divide it into 2 functions, that is these 2. And then I look at, say the value of x naught is anything. I can put this is just for an assumption. Say the value of x naught is 2. Okay. So for values less than 2, okay, this x is not very significant, okay, in front of x naught. So we can kind of, approximate that this is almost equal to 1 by x naught. Okay. Or say this value of x naught is 20 or something, and my value of, say, x is equal to, say, around 0.01. So it's not really significant, doesn't really make a difference. So I can approximate my function as 1 by x naught. Okay. So then the only thing that kind of governs, how this function looks like is x. So I know that initially, that is for very low values of x, this is what will govern, how my function looks like, because this is almost a constant. So I can, and what the graph of y equals x looks like is just a straight line. Okay, it looks like a straight line. But afterwards, since you know that, so in a sense it's like 2 different gears. Okay, when x is very small, this gear works. Okay, when x becomes greater and greater, and significant, it actually starts making a significant difference to your this gear comes into play. And then it's a mixture of both of these functions. So since we know that at the start we have like a straight line, this would later on join this function, and this would look something like this. So this is one way of doing it. If you find it very confusing, there's another way of doing it, where you have to, so another way of doing is the slope. Okay, the slope, how do you look at, so slope tells you what? It is the rate of increase in the function. Okay, so you want to know how does the function increase. So can anybody tell me what is the derivative of gx?
So that partial derivative, that rule has to be applied. No?
Yes. Can you tell me that rule? Do you remember? Does anybody remember?
So one minute, I've written it down.
Yeah, go ahead.
So the denominator squared, and then then the denominator into the derivative of the first.
Okay, so denominator into the derivative of x is 1.
1, yeah. Minus, yeah.
The numerator into the derivative of the denominator, which is 1 again. So this gives me, this gets cancelled. It gives me x naught by x plus x naught square. Okay, so now if you look at this, you see that the rate at which the function increases, this is the rate at which the function is increasing, the first derivative. Okay, so the rate at which the function changes, sorry, not decreases or increases, but changes, we know that this is greater than 0 firstly. So we know that the function would be increasing. Why it is greater than 0? We know that x naught is greater than 0 and the square of anything is greater than 0. So one thing we know is that this is greater than 0. Secondly, what if I increase my x? So when my x increases, just remove this. When my x increases, my denominator becomes bigger and bigger. That means that the rate of increase decreases. Okay, it decreases. Is this clear?
Yes.
So it is still increasing, but as you're increasing your x, it's increasing more and more slowly. So just to make it make you understand this visually. So here my rate is like this. Okay, look at the slope. But when I go here, the slope is decreasing. As I go here, my slope is again decreasing. So in a sense, the rate of increase is slowing down. So this is another way of thinking about how do you plot the function and how would the function look like. I hope this is clear. I think it is.
Yes.
Okay, so one more thing I think we forgot, which is the root of the function of gx. What would be the root of gx? I think this should be simple. What would be the root is where the function gx becomes 0. At what point do you think the function would become 0? Hello, people. I can't hear you.
When x equal to 0.
Exactly. Yeah, great. So at x equals 0, if anybody got this correct, very good. So at x equals 0, the function becomes 0. Great. So we have kind of, figured out, okay, this is how my function would look like. But can I rub all these things? Is that okay?
Yes.
Yeah, it's okay, no? Okay. So these are just two ways of doing it. One is through using the derivative. The other one is using the gear and all these kind of it's just a way of thinking about the function. Okay, so now we know that my function looks like this. Okay, and we know that, so we want to find So, okay, I had actually kind of removed the h from here, okay? Now, when I introduce h here, what would happen to my graph? What would happen to my plot?
It will just shift upwards.
Yes, instead of 1 here, this would be some h, okay? So the function would try to reach, the value h, yeah, instead of 1. Yeah.
Equilibrium.
Equilibrium will come to. I think that is something Vishu will cover in the next class. Okay, so now we want to find the points of intersection of these two graphs. We know that my parabola looks something like this, okay? And we know my gx, this is my fx, and okay, f function fx, and this is my gx. So before plotting my gx, can you guess how many, what would be the minimum and maximum number of points of intersection that I can get? In a sense, you have to kind of superimpose these two functions, okay? And depending on the value of x, depending on the value of h, right now I'm just considering h, okay? I can also consider r, but because we'll do that also if you want. Or you guys can try, I think. So here what I'm doing is I am plotting this parabola, okay? I'm kind of fixing this parabola, and then I'll plot h over it, like in some ways, okay? So can you just make a guess, how many points of intersection will you get when you plot these two graphs together?
A maximum of 3.
Yes. Does everybody agree with that?
Yes.
Maximum would be 3 and minimum?
1.
Minimum would be?
1.
1. Okay, let's try. Okay. So here, yeah. So for example, my h is very small. Say my h is somewhere over here, like very, very, very small. So my graph would go somewhere like this, and it would intersect like this, okay? So here, firstly, I have this point of intersection and this point of intersection. So I have 2 points of intersection. Similarly, my h could go like this. Again, I have this point of intersection and this point of intersection. Alternatively, I can have something like this, which gives me 1, 2, and 3 points of intersection. Okay. I can also have a graph which is kind of similar to that, the straight line also, that straight line example, which could be, tangent at 0, and it could go like this. Okay. Again, we would have 3. There could also be 1 point of intersection, which actually kind of, becomes tangent to this. Okay. So here I have this x equals 0 as one of the points of intersection, and I can have one more here. Okay. And beyond this, basically, after, again, there is, okay, I think use some other color. So beyond this, so you see this line, this is like the tangent to the function. So beyond this function, beyond this tangent line, if I increase my h, increase my h or something else, I'm not sure about it right now. So if I go, if I make my function go like this, it might never even touch it. It might never touch the parabola. So here again, we have just 1 point of intersection. So depending on how I change my h, I can either get 3 points of intersection, or 1, or even 2. I can even get 2. Okay, so something what you guys can try is you actually plot the gx function first, and then keep changing the parabola. Okay, you plot this function first and now keep changing. So there would be some value that would be changing. Okay, for example, I can plot it like this. I can even plot it like this. And yeah, I mean, obviously some things would be okay. I think this, if I keep it as k, and if I change just the slope of the function, it might be like this, something like this. So you can play around with these things. Is this clear? How do we look at two functions together?
Yes.
Yes, great. Okay, now I hope it is clear. If you don't have, you can ask me later on. So we are done with this also. Now we come to the very interesting third part of this question, which is, I don't know, this is a scary function. Like, I would call it a scary function. Scary looking. Okay, so now my gx is similar to the previous function, but it's slightly different. So this is x square plus x square, x naught square. Now again, we'll do the same things. What should we do first? Come on. Somebody. What should we first look at? I would like to call out somebody's name now. If nobody.
Domain and range.
We can, yes, we can find the domain and range. So what would be the domain? So what are the values that x can take? Okay. Firstly. Can x take any values?
X can take all real numbers.
Yes, x can take all real numbers. This is how it is denoted. That's, you might find it there in maths textbooks and all. Okay, x can take all values. Now, if I ignore h again for some time, what are the values that my gx can take? I think one thing is there, whenever you see x square or square of a lot of things, it should be very clear that it would be a positive number. Okay, so I know that my gx would be greater than 0. What else? What else can you look at and tell me that, yeah, it's kind of similar to the previous question.
This function is also tending to 1 as the value of x increases.
Exactly. So as x increases, I know that, the numerator becomes really large, but the denominator also becomes really large. But the denominator would always be slightly larger than the numerator. So it would always be tending towards 1. Okay. But when I add h here, it would always be tending towards
H.
Okay, great. Okay, here is a very interesting, I like this example for one thing. I'll tell you now. So these things are done. Okay, can you tell me the root? The root is very obvious here. What is the root of this? At what point is this function equal to 0?
When x equal to 0.
Great. At x equals 0, this function is 0. Great. So I know that one of the roots is x equals 0. This is my x. This is my x. Okay. Now, I'll take the same example. I'll take the same approach. Okay, you can try. We'll try with the derivative approach. So I know again that this would be tending towards 1. Okay, something like this. But I don't know how would this increase. How would this, what would this increase look like? So let's take the derivative first. Okay. Can anybody tell me what would be the derivative of this?
So the same rule we have to apply x square.
Yeah. Okay, I'll just do it for now.
X square minus whole square.
Yeah. Then the
2x h.
yes, the x square plus x naught square minus of the
hx square.
oh yeah, h I keep out. Okay, I mean in general, x square and then again 2x.
Yeah.
Which is the derivative of the denominator. Now I can easily just cancel these two things. What I get is, I keep h separate for now. I get 2x x naught square x square plus x naught square whole square. So now you see that as x, so there's a dependence on x now. If you see here, because you have, so as your x increases, as my x increases, the denominator actually increases a lot, but also my numerator increases. Okay. But my denominator increases, what do you say, at a much higher rate. So for some reason, I really don't like this approach. I mean, for this case, okay. It does tell me some things, okay, that, you know, the rate increases, but the rate is slow, okay. Now we'll take the other approach that I mentioned, which was actually kind of looking at gx as the product of two functions, square plus x naught square. So again, for example, my x is, you know, my x is much smaller than x naught. For those values of x, I can consider this as 1 by x naught square, almost, for values which for of x which where it is very small. Okay, then what I get is my function becomes like a parabola. Okay, so what governs my function here is just x square. So I can, what does a parabola look like? How does a, I hope you guys remember how does the function of x square looks like. It looks like this. Okay, so I know that for the initial values of x, the graph would somewhat look like this. Okay, so that's what I'll do. For very small values of x, the graph would look something like this. Okay, but soon my x would increase. Okay, my x would become greater and greater, and I can no more take this approximation. Okay, this approximation, this one. So now, in a sense, what we'll do is, shit. So this look like this, like the value of x square, and then I know that after that, this denominator also comes into play, and it would somewhere join. And I know that the rate. So here also, if you look at this, expression that we get, yeah, you get that as x increases, my gx also, my gx decreases. Okay, as in it becomes slow, but I know that initially the increase would look like what an x square increase would look like. So later on, I know that this would go somewhere like this. So it's very different from our function, which was before, where the increase was more linear because we had an x here. So look at this, and because we had x, and look at this because we have an x square here. So this is the basic difference between the two functions that we have. Okay, so now for this,
can you please show it again to me? The difference, that difference.
Okay, I'll show. Actually, wait. I'll show you. Okay, so the difference is here. Look at this part of the function. Okay, sorry. Look at this part of the function. Okay, the increase here. So your the in the previous somewhat like this. Okay, it's increase is linear.
Others, please mute. I mean, there's some disturbance, I guess.
Yes, please mute. Yes. or I can mute everybody also. Okay. So the thing is, in that case, the initial increase looks very linear. Okay, because you have a g instead of x square here, you have x. So the increase would look linear. But here, because you have x square, the initial increase is it's like a parabola initially when your x is really small. You can actually plot this and also see. We'll do that also.
Okay. Got it.
Okay. But did you get the difference? It's about this part.
Yes.
Essentially about, yeah. It's essentially about just this part. And it's important because I think, I don't know, did Shoaib talk about some functional responses and all? So these are two different kind of functional responses that you see in nature. That initially some increase is not that, some increase in some value is very slow, and then suddenly it becomes very fast. Like slow, the increase is very slow here, and suddenly it becomes very fast. Whereas here it's kind of linear, and then it becomes slow, kind of like that. Okay, I think we are kind of running out of time. I'll just can you guys just similar to the previous one, can you guys plot something like this and tell me how many points of intersection will you find in this case? I'll just plot these two. Okay. I think it should be simple now. How do you plot these two graphs? So one is my parabola. Okay. And the other one is this graph. So I'm just plotting for one of the values of h. Okay. So it could go like this. Or it could go like this. I mean, you can play around and see how many points of intersection you find. Would you guys be able to do this?
I mean, do as in after the class, or I mean, I didn't understand. Sorry.
Yeah, after the class. I mean, would you be able to do it on your own?
Yes.
Yeah, I will try.
Okay. You just have to assume, you know that the function looks like this, the blue function. You know that it looks something like this. So it can go like this. It can go like this, and just imagine. It can also be somewhere like a tangent also. So you just have to play around with, it's just playing around with the imagination what my function could look like if I increase h. Okay. Or you can do the other way around also. You can plot the gx function first, this function first, and then plot the parabola. Since we have not defined the values of r and k, so you can really play around here. It's not defined. Okay. So I hope these were clear to you. We have covered. Does anybody have any question?
No,
okay. No. Okay. So were you guys able to try question number 4 and 5?
Yes.
Okay. How many of you were able to do it? Can you just raise your hand so that I can see if... Okay, I see Raghuram's hand is up. Okay, only Raghuram. Okay. Did you guys... can you tell me where was the problem, or have you not tried it yet? Okay, in case if you were able to
try the second one.
You didn't try the second one, you mean this factorial one? Okay, it's fine. If I think it would be helpful if you can try and see. I don't know if the last class was really helpful, but okay, in this class I want to cover would you guys have a little more time? I just want to cover two things in R, which is plotting and functions. And Okay, let's try. I don't know how much I can cover in that. Okay, I've stopped sharing my screen quickly. I'll share this screen. Okay, can you see RStudio?
Yes.
Okay, if in case you were not able to do the factorial one, it's okay. I mean, you can look here, but yeah, it won't be good for you. It's best if you can do it on your own. Yeah. Okay, I'll start with the plotting and all. So for in R, you already have a factorial function. Okay, I hope but you know what a factorial is. A factorial is, for example, if I want to find 5 factorial, it looks like this: 5 with a exclamation mark. It is equal to 1 into 2 into 3 into 4 into 5. That is 5. Okay, so you already have a function which tells you the factorial. It's called factorial, obviously. So if I want to find the factorial of 5, I'll use this function factorial, put number 5 and do control enter, and this is the my console will show me the value 120. Okay, so now for example, I want to plot a graph of where on my x-axis I have the value of n, which is the number that which is the argument. So the value that you pass into a function is called an argument. So the argument that I pass into this function factorial is given on I want it to be on the x-axis and the factorial to be on the y-axis. And I want to plot this graph. So what I do is I will make a kind of a vector or a list of a list of numbers which have numbers 1, 2, 3, 4, 5. So I can either make it just simply like 1 to 5. Okay. So I get my this thing, my vector n, which has values 1 to 5. Or I can also make using the sequence function that we talked about last time. The starting point of the sequence is 1, the end point is 5, the steps in which I want it to increase should be 1, and I do control enter, and again I get I hope my cursor is visible. I get my this thing n as the sequence of 1 to 5. So I can use either of these approach. Okay. Now, so this is my x. Okay. This is my the values for x for my plot. Even these are. Now I want the values for y. So what you can do is you can either save it as another variable, say y, and for y, what we'll do is, since we need to find the factorial of each of these elements of n, that is 1, 2, 3, 4, 5. So what I can do is I can pass the vector into the function factorial. Okay, so I am actually passing this vector into this function, and what it would give me is another vector with the values, that is which is the values of each of the elements of vector n. So 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial is equal to 3. So the thing is, you can just pass a vector into these functions and it would automatically do it. Okay, and I have saved all of this whole vector in a vector called y. So these are my values of y. Now, very simply, how do you plot it? You say plot, and you can see this yellow box, right? It actually prompts you, what values you have to add. So first you'll put the vector which has the values of x. So which is the vector which has the values of x?
N.
N.
N. Great. So I'll put n. And then you have to put the vector
Y.
which has all the values of y, which is y here. Okay. So very simply, I'll just do control enter. So here, if you see on the right hand side, you see that my plot has been so it has pointed so it has plotted points. Okay. So what I would like to see is I would want to see a line instead of points. So by default, it shows points. So for example, I want line. So you have to put type. So in type, if I put L stands for line, and I do again control enter, it gives me a line. So in some cases, you would want to have both. You would want to have both points and lines. So simply instead of L, you would put B and do control enter. So it shows both points and lines. For just showing the points, you can either leave it as it is or you can put B. Okay. So there are other values also you can put, but for now I would like to have L. So I'm putting L. Okay. Now, for example, if you want to plot another, so even in the plot function, you can give a lot of details. What do you want to add? For example, I don't want my x-axis label. I want to give a nice label to this. So I would say, so it would.
Tanveen, I had a clarification. I mean, so I don't know. These things can be done even in Excel or something, right? I mean, why would you use R only for plotting and things like that? I mean, what is the?
No, so the thing is, for some of the functions, right? For example, finding, I think factorial might be easy, but there might be some functions that you would define in R. Okay. So here I'm using the function factorial, right? For other, there would be some other function that you would.
Something logarithmic or exponential, anything.
Yeah.
Okay. So this factorial is not a built, it's not a built-in function, right? Or
It's a built-in function. It's a built-in function.
Okay.
I haven't made it. But the thing is good. Yeah. The next thing that I would cover is actually defining your own functions. Okay. So you can also define your own functions and use them. So R is, nice that way. And even for other simulations also, R is a nice, you would come across a lot of things that, for example, a lot of iterations and all, right? I think that you can't do in Excel and all.
Okay.
For example, you have a big list and you want to apply some operation to each of the values. It's like many iterations, and then get a list of other values. So those things are easy in R or any programming language for that.
Okay. Got it. Thanks.
Yeah. So I'm just telling you basic things. It's if you're able to do this, it's actually well and good because you can actually visualize your data and we can also try with the functions. You can actually try all of these things, the plot function, for all the functions that we have tried today. We actually tried it by hand. You can actually do it in R and see how does it look like. So I think that would be a good exercise. Okay, I'll just quickly go tell you, you can use these things. And especially how do you plot two functions in the same graph? That I want to cover. It's going to be 5. I think I'll take maximum 10 more minutes and then we can finish off. We should end the class. Cool. Okay. So yeah, to give X label, I can give, say, number of students or something like that. And Y label would be, because I'm here calculating factorial, and then so Y lab is Y label. If you want to give a title to the whole, the whole plot, you can put it under main. So you can say my plot of n versus factorial, something like that. And yeah, okay, I think it's, yeah. So now I do control enter. So you see here you get factorial, you see number of students, plot of n versus this. Okay. And okay, so for example, if you want to plot another graph on this, let's take, I want to plot, say the square of these elements of n. Okay, so I'll define a new list which says n square. If you remember from the last class, you can simply do these arithmetic operations on these vectors, and what it does is it performs that arithmetic operation on each of the elements of the list or the vector. So when I do square equals n square, it performs that function for, I've already done this, that's why it shows like this. So I did control enter. Okay, so what it shows is square of each of these elements. So what I want to do is now I want to plot these the same the square function on the same plot. So I can do it two ways. Okay, I can either plot points, okay, or I can plot line. So if you want to plot points, you use the function points. So again, it would ask you what is the x-axis, what are the values of x, you put n, but now my y-axis, sorry, my y values are given by the list or the vector square. Okay, and so that we can differentiate it, I give it color. I give it the color red, so it is distinguishable from that. And I do control enter. So you can see that the elements of this square vector appear here. Now, if you want line, you would put lines. I think so, yeah. Similarly, as just like the points thing, the points function, you put n, you put square, and the color I put as green. Okay. As simple as that. So now it shows a line which is green in color. Okay, now first, sometimes you would want to actually plot lines, which are say perpendicular to, say, I want to plot a line here at x equals 3.
I mean, are there examples like this in the help or something? I mean, we may not remember the entire syntax and things like that.
Yeah. I think there are. We can try actually.
Okay.
Actually, I'll send you a tutorial. It's not a tutorial. It's like a documentation of R. You don't really have to. So the thing with R is you can find a lot of if you have any trouble with R, for example, you want to do something, you just Google search it. Okay, you would find a lot of assistance online. A lot of, because the community is very well. It's a very big community and a lot of people use R. So you can always find help. You can actually, a lot of times you'll get a warning. Okay. So what you can do is you can just copy paste that warning and yeah. And you can search. So they will tell you, where, you might be making a mistake. So I think that is another thing which is good with that, a lot of people are using it and you would be able to troubleshoot it.
Okay. And the other thing is I don't get this auto filling things in Windows. Is there some setting that's, I mean, I'm just asking others who are using Windows, if there's any setting to be done to use this auto filling, because I don't get anything. I have to type the whole thing.
Oh, I don't know actually. Yeah,
that's what I asked others if there's somebody's using Windows and if some settings need to be done or something. I couldn't. Okay, I'll find out.
Yeah, I think you can take help from Arun. Arun is kind of the expert with all these technological, stuff. Yeah, he's also one of the TAs. Okay, so we are done with this. So a lot of times you would want, to plot a line which goes through x equals 3, like a perpendicular line. So for that you'll use AB line. Okay, and so for example, if you want a horizontal line, you type H. If you want to have a vertical line, you type V. So if I say I want a vertical line which passes through 3, x equals 3. So I do this. I give the color as blue. So this is what it gives me. Okay. Similarly, you can do it for like a horizontal line. Okay. H equals, say, I'll do 80. And color, I'll do gray. And okay, so you have a line here. So this is like very basic plotting and all. Okay. I think I would really suggest that you try plotting the graphs that we have done today. I think for that, I'll quickly tell you how to. So the question, one of the questions in the assignment was that you have to calculate the factorial, right? So for example, if a function for factorial didn't exist in R, what do you do? So for example, I have written this. This is how my function would calculate the value of factorial. Okay. So how do I define a function? So I define a function fact for factorial, and how do I define this? Is I say function. Okay. So it gives you all these details. So in this bracket, you put what value do you want from the as the input. So the value that I would want for the input is the value n. Okay. And after this, you write the body of the function, which is how would you even calculate this? So this is my code for how am I going to, compute the factorial of a function, factorial of some number. Okay. So just so that you don't get confused, what I do is I take this value and save it in value g, which I equate to 0. Then what I do is I iteratively keep multiplying my g into n minus 1, and so this is some function that I wrote that I know will give me the factorial. And whatever you want to return as a result of this function, you put it in the end. So what I want my function to return is the value of g once it is done. Okay, and I press Control Enter. So now you see here it shows that in your environment you have one function called fact, and this function takes n as the argument. So let's try. So I know that the factorial function already exists. So just remember that when you're defining a function, you give the function name, you put equal to, you put function, and then the argument. The argument can be more than one also. For example, in the plot function, you give so many arguments, right? You give the value of x, y, and all these things, right? So the arguments can be one or more than one, and even 0 sometimes. Okay, and then you actually tell the function, what exactly it has to do. So let's calculate the value of factorial of 5 and see if my function really works. So from this, I know that factorial 5 is equal to 120. We can see in the console. Okay, now I'll try with my function fact. So now it's showing it right as another function. So I'll put 5. I don't know if it will work. And I do Control Enter, and it shows me 120. That means my function is working. Okay, so this is how you define a function. So for one of these, the problems that we had solved today. So this is the last thing I'll cover. You guys are free to go after this. I'll just tell you, we can try writing, say the first GX, which was, what was that? Actually, those might be, you can write it directly also. So I'll say define a function gx. Actually, I can define it simply also. Like it would be x divided by x plus x naught. yeah, you really don't have to create a function, but yeah, when you really have these loops or something like that, at that time you would want to create a function. So this I've anyway, you can use this function and actually, okay. Yeah, okay, let's try actually, sorry. Let's try to make a function which takes the argument x, okay? And now I define the body, okay? What does the function do after taking the value of x? What it does is it returns, so you don't really have to write return, but what it computes is, it computes, so it can actually take two values, x and x naught. So x divided by x plus x naught. So when you do this, I have defined this function, okay? Now I want to know what is the value of this gx at, give me some number.
5.
5, and give me some value of x naught.
9.
It could be 9, okay. Okay, so it gives me a value of this. Great. So you can do this, and actually you can plot this, you can actually try plotting these functions in R and see if you actually get the same result as as you found when we were actually doing it by hand. So I hope you would be able to use R now. Just play around with it. Whenever you need help, just do question mark plot. You would find, yeah, you would find here. They also give examples. For example, here I've tried type, right? You can try this main. You can also give a subtitle and all these things. You can try these examples also. And so this is like the basic of functions and plotting. Cool. I think we should end the class now, unless you guys have any doubt. Do you have any doubt? I don't know how many people are left also. Okay, cool. Let me know if you have any doubts or anything. Great.
Thank you.
Cool.
Thank
Great.
you.
Okay. Bye-bye.
Bye.
Stop the recording. Yeah.
Bye.
Thanks. Yeah.
Hey Arun, are you there?